Hello, students. I did have someone ask a question about chapter 4, question number 15. So let's take a look there. Oops, question 15. So the question here was about finding the a particular number, the least non-zero number that's divisible by every non-zero whole number less than or equal to 10. So you could certainly list out those numbers and kind of figure out exactly which numbers we're talking about. So every whole number less than or equal to 10. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, less than or equal to 10. So include 10. So let's see here. We need to find a number that divides all of these. So D has to divide every single one of these individual numbers. That means in order for that to happen, we need to find, divisible by. I got that backwards. Not divides into, but divisible by. Divisible by. So these numbers have to divide into our number. So this number over here is a multiple of all of these numbers. That means it has to be a multiple of 2, a multiple of 3, a multiple of 4, because that 2 has to be a divisor of. So let's see, we need a multiple of all. That means for all these numbers, we're basically finding the least common multiple because it is the least non-zero number that does all of those. So LCM. So if I was going to do this problem, I would probably go through and find my prime factorization. So 2 is just 2 to the first, 3 is 3 to the first, 4 is 2 squared, 5 is 5 to the first, 6 is 2 times 3, both with an exponent of 1. Let's see here, 7 equals 7 to the first, 8 is 2 to the third, 9 is 3 squared, and 10 is 2 times 5. So again, I want the LCM of all of these. So the LCM of, I'm just going to say yada, 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 right? All these little pieces here. The LCM of all those things, I'm going to choose the highest exponent for each of the primes. So when I look at 2, there's definitely a 2, the highest prime. There's 2 to the 1, 2 squared, 2 cubed, so it has to be 2 to the 3. For 3s, oh, there's a 2 to the first, and there's a 2 to the first again. I need to go to the 3s now. There's a 1 there, a 1 here, and a 2 here. So I choose the largest, which is 2. And then we've got 5s. There's 1, 5. That's the most, so I choose 1, 5. And then 7, I have 1, 7. So this really right here, this would be the least common multiple of all of those numbers. And basically then every single one of those numbers would divide into our number. So let's see here. 2 cubed is 8. So this becomes 8 times 9 times 5 times 7. And I get 2,520. So there's my 2520 would be my final answer. And that means, does 2 divide it? Yes. Does 3 divide it? Yes. Does 4? Yes. Does 5? Yes. Does 6? Yes. 7, 8, 9, and 10. Every one of them divides this number. And there is no number smaller than this that would actually do that because we've chosen the biggest exponent possible here. So if we chose any smaller exponent on any of these, one of our numbers would fail. So that kind of helps hopefully with that. When you have long lists of numbers and you're trying to find the least common multiple of those, I think it's probably the best idea to do the prime factorization. It just makes it a little bit easier. The list method would be horrible on that one. It's absolute nightmare. That would be kind of my recommendation there. And let's see here. We also want to check. Let's see here. What else? Oh, we had a question about how do I find the number of divisors? Okay, so let's see here. We have a few in here. This would be number of positive divisors, like number 7 here. Find all the positive divisors, or maybe just find how many divisors it has. So why don't I just share a blank screen here and we'll do an example. So if we have, let's see here, 2 to the 50th times 7 to the 20th, and you want to know how many total factors there are. Remember, the number of things that divide the 2 to the 50 would be 2 to the 0, 2 to the 1, 2 to the 2, all the way up to 2 to the 50. So there's 51 factors from this. There's 21 factors here for a grand total of, and the reason we're multiplying is because for each one of these 2 powers of 2, I could put those together with a power of 7. So for each one, for every. So that's why there's 51 times 21, and I get 1071. So that's how many different factors you could have there. So again, that's why we add 1. In class, we did one that was like a 2 cubed times 3 plus 2 times 3 squared times 5 or something like this. And here, what I want you to realize is if you're trying to find prime factorization, you have to get rid of things like addition. You cannot have addition if you're going to do prime factorization. The word is factorization. So that means I need to look for things that are in common. And so in common, I see 2s and 3s. So 2 to the first is the biggest one I can get out of both of those. And 3 to the first, that's again the biggest I can get out of there. And what remains then is a 2 squared plus 3 times 5. And then let's see here, 2 times 3, 2 squared is 4, 5 times 3 is 15. So notice I still have addition, so I have to keep going. And I have 2 to the first times 3 to the first times 19. Turns out 19 is prime, so my final result would be something like this. So there's my final result. If you wanted to find the number of prime factors from this, then now at the end we could go down and say 1 plus 1 is 2, 1 plus 1 is 2, 1 plus 1 is 2, and 2 times 2 times 2 is 8. So this number has 8 different unique positive divisors. So let's see here. What if we did something crazy? What if we did like a 2, 2 to the 50 plus, I don't know, 7 to the 20 or something like that. So now this is one that's a good question because it says, well, wait a minute, I need prime factorization, but I have addition and there are no common factors. So the only thing that you really could do here is to multiply all of these numbers out and then add them all together. And let me just see here, 7 raised to the 20th power. This part by itself is 7.9792 ... times 10 to the 16th power, which is, we will never even know all the digits unless we multiply this out by hand. And this number is 17 digits long. Then I'd have to add it to 2 to the 50th, and 2 to the 50th is 16 digits long. So again, this is not a question that's not only is it not easy, it's that it's quite challenging and very tedious. So that's why we typically don't see that question asked in the textbook. So maybe it was just like a what if question, but this is not something that that we would really have the tools or the time to do. It would just be very, very tedious as we do it. Okay. Well, hopefully that helps. Let me jump back. I think that's the last piece of it related, kind of to the textbook. And yeah, there you go. So again, if you do see common factors and you're trying to find prime factorization like you have down here in number like 14, look for prime factors. But if it's 2 things that are added together, factor them out, turn it into multiplication, because that's what prime factorization really represents. All right. All right, that's it for now. Off you go.